Geometric series in general is a summation of a series, but then there are some ratio r. It can be written in the form summation of n equals 1 to infinity of a r raised to n minus 1, or with an index shift, the geometric series will often be written as summation of n equals 0 to infinity of a r raised to n.
So for example, if you express out the first few terms of this, the first one, you plug in n is equals to 1. So r raised to 0 was 1, so a. And then when you plug in n is equals to 2, you get r1, so ar plus ar. And so on. And so now this converge or does this diverge? So it depends on the parameters. We'll consider this. I wrote down S sub n, the partial sum, and the nth partial sum is sum of a plus ar squared all the way to ar raised to n minus 1. So to perform a little algebraic trick here, let me take this s sub n and let me multiply r to it. So let's consider r times s sub n. So a turns into ar turns into ar squared turns into ar cubed, all the way to the final one, which is ar raised to n. Now I got the s sub n and r times s sub n. And let me take the difference. Let me look at what the partial sum minus r times the partial sum gonna be. Indeed, this is plug in for the s sub n. And I take the r times s sub n and subtract that off. Now there is an enormous amount of cancellation. So for example, you see that there's a plus ar and a minus ar, then those two terms are gonna cancel. Then there's a plus ar squared and a minus ar squared. Those two also are gonna cancel. Then somewhere in the dot dot dot, there be a positive ar cubed, then there's a minus ar cubed to cancel. And finally, in the dot dot dot, there is a subtraction of ar and minus 1. So that's gonna cancel. So what do I have left here? The only thing remain is a minus ar raised to n. Now, if I focus on a special case, which is r is not equal to 1, then I can divide by 1 minus r and just get my partial sum, a minus ar to the power of n over 1 minus r. So these series converge. The series converges by definition, that thus the limit of the partial sums converge. So limit as n approaches to infinity, the partial sum is equals to limit as n approaches to infinity, a minus ar to the power of n over 1 minus r. So it depends on the value of r. So if the absolute value of r is greater than or equal to 1, then it diverges. But if the absolute value of r is less than 1, then it converges. Example: 9 to the power of negative n plus 2 times 4 to the power of n plus 1. So let's first rewrite this, because one of the n's in the exponent has a negative in front of it and that can't be there in a geometric form. So we will rewrite it as 9 to the power of negative n minus 2 times 4 to the power of n plus 1. And then 4 to the power of n plus 1 over 9 to the power of n minus 2. And then we can get the correct exponent on each of the numbers. These can be done using simple exponent properties. So 4 to the power of n minus 1 times 4 to the power of 2 over 9 to the power of n minus 1 times 9 to the power of negative 1. And then we write the term 16, which is this, times 9, this, times 4 to the power of n minus 1 over 9 to the power of n minus 1. And then multiply 144 times 4 to the over 9 to the power of n minus 1. So this is a geometric series with a as 144 and r, which is 4 over 9, which is less than 1. Therefore, this series converges. Example number 2. In this example, I am using the form a r to the power of n. So 5 to the power of n minus 1 times 9 over 10 to the power of n. So we can write it as 5 to the power of n times 5 to the power of negative 1 times 9 over 10 to the power of n. So 5 to the power of negative 1 is the same as 1/5. So we can write it as 1/5 times, we have the same exponent, so 5 times 9 over 10 to the power of n. Then 1/5 times this one, which is 9 halves to the power of n. So now we can rewrite it as 1/5 times 9 halves to the power of n. And now we can find the value of r. The value of r is 9 halves, which is greater than 1. So it means that this series diverges.
Telescoping series. A series where all terms cancel out except for the first and last one. This makes such series easy to analyze.
Consider the series which starts from 1 and goes to infinity with the sequence 1 over n plus 1 minus 1 over n plus 2. So will this series converge or will it diverge? So we need to determine if this series has a finite sum, and if it has a finite sum, that means that it's going to converge. But if it goes to infinity or negative infinity or it doesn't exist, then it's going to diverge. So how can we determine the sum of this particular infinite series? So what we have right now is a sub n. A sub n. The sequence which gives us a list of terms in the sequence, and what we need to do is find a general formula for S sub n, the partial sum of the sequence. And if we take the limit as n approaches to infinity for the partial sum formula, that will give us S. And so, we need to determine if this infinity or is it a finite number. And this is equal to the sum of the series, this one and this one. So, how can we do that? Well, let's begin by listing out the terms of the sequence. So, the first term, a sub 1, if we plug in 1 into this expression, n plus 1 is 2, minus n plus 2 is 3. So this entire thing is the first term. First term. Now, the second term, a sub 2, if we plug in 2 into n plus 1, that's gonna be 3. And then, if we plug in 2 here, 2 plus 2 is 4. So this a sub 2, the second term. This is a sub 2. So let's find the third term. So 3 plus 1 is 4. And 3 plus 2 is 5. So this becomes 1 over 4 and 1 over 5. And so this is a sub 3. And then this will keep going. Now let's get the a sub n minus 2. So, a sub n minus 2. So replace n with n minus 2. So we have n minus 2 plus 1. So that's gonna be n minus 1. And then n minus 2 plus 2, that's simply n. Now let's get the a sub n minus 1. A sub n minus 1. N minus 1 plus 1, that's just n. And then n minus 1 plus 2, that's n plus 1. And finally, the last term of the sequence is a sub n. And a sub n is what you see here. This is a sub n. So that's just gonna be 1 over n plus 1 minus 1 over n plus 2. So notice that these two cancel, and then these two cancel, and negative 1/5 will cancel something in the series, and then 1 over n minus 1 will cancel something else, and then negative 1 over n and 1 over n will cancel, and these two cancel. So the only two things that didn't cancel is the first term and the last term of the sequence. So now, this gives us a general formula for S sub n, which is 1/2 minus 1 over n plus 2. Now, once you have the general formula for a sub n, take the limit as n approaches to infinity for the partial sum formula. And so, we have the limit as n approaches to infinity of 1 over 2 minus 1 over n plus 2. So, this is equal to 1 over 2 minus limit as n approaches to infinity of 1 over n plus 2. So, now, for 1 over n, as n approaches to infinity, that's gonna go to 0. So, 1 over n plus 2 will also go to 0. So, this is going to be 1/2 minus 0, which is 1/2. So, this is the sum of a series as n goes to infinity. So, because the sum is equal to a finite number, we could then say that this series converges. Now let's try another problem. So let's say the sequence is 1 over n times n plus 1. So you know that this is a telescoping series. So therefore you know that this is some type of telescoping problem. But if you start plugging numbers in, this is what you're gonna get. So if you plug in 1, it's gonna be 1/2. And if you plug in 2, it's gonna be 1/6. And if you plug in 3, it's gonna be 1/12, and so on and so forth. So this doesn't look like the telescoping series. And the reason for that is we need to change the form of the problem. What we need to do is take this fraction and decompose it into two simple fractions. So So we need to use partial fraction decomposition. So we're gonna set this fraction into a over n plus b over n plus 1. So what we need to do is determine the values of a and b. So what I'm going to do is I will multiply both sides of the equation by n times n plus 1. n plus 1. So when I multiply this fraction by that expression, these will cancel. So I'm just gonna get 1 on the left side. So a over n multiplied by n times n plus 1, n will cancel, giving me a times n plus 1. And then if I take this fraction multiplied by n times n plus 1, the n plus 1 factor will cancel and leave behind bn. bn multiplied by n. So what I'm gonna do is plug in 0 into this expression so that this will disappear. So when n is equals to 0, I'm gonna have 1 is equals to a, 0 plus 1. 1 is equals to a, 1. So a is equals to 1. Now, when n is negative 1, a multiplied by n plus 1 will disappear. So 1 is equals to b times negative 1. 1 is equals to negative b. So b is equal to negative 1. So therefore, I can rewrite the series like this. This is gonna be a over n, which is a is 1, so 1 over n. And then it was plus b over n plus 1, so b is negative 1. And then over n plus 1. So let's begin by listing out the terms. So when n is equal to 1, the first term will be 1 over 1 minus 1 over 2 plus the second term a sub 2, so it's gonna be 1 over 2 minus 1 over 3, and let's move on to the third term. Plug in 3, so it's gonna be 1 over 3 minus 1 over 4. Now, let's get the a sub n minus 1. So we place an n with n minus 1, so we're gonna have this, and then n minus 1 plus 1, so that's gonna be n, so it's 1 over n. And finally, the last term is a sub n, which is exactly what we can see here. So 1 over n minus 1 over n plus 1. So all of this is equal to s sub n. This is a sub 1, a sub 2, a sub 3, a sub n minus 1, and a sub n. Now, let's simplify the expression so we could cancel negative 1/2 and 1/2, negative 1/3 and 1/3, negative 1/4, which is somewhere in the middle of the sequence. And we can also cancel something here with 1 over n minus 1 and negative 1 over n and 1 over n. So we are left with the first term, which is 1, and the last term, which is negative 1 over n plus 1. Once you have the general formula, take the limit as n approaches to infinity for the partial sum formula. And so we have the limit as n approaches to infinity of 1 minus 1 over n plus 1. So this is equal to 1 minus the limit as n approaches to infinity, 1 over n plus 1. So now for 1 over n, as n approaches to infinity, that's gonna go to 0. So 1 over n plus 1 will also go to 0. So this is going to be 1 minus 0, which is equal to 1. So this is the sum of the series as n goes to infinity. So because the sum is equal to a finite number, we could then say that the series converges. Now, we'll talk about one of the most famous infinite series, which is the harmonic series. The harmonic series is the summation from n equals 1 to infinity of 1 over n. So if we expand this, we would have 1 plus 1 half plus 1 third plus 1 fourth and so on. And these series diverges even though the terms do approach 0. And we can show this as long as we recognize that the summation from n equals 1 to infinity of 1 half diverges. Since we're adding more and more 1 halves together, and therefore the sum would approach positive infinity. Now, using the harmonic series, we can group the terms so each partial sum is greater than or equal to 1 half. So again, if we expand the harmonic series, it is equal to 1, which is greater than 1 half, plus 1 half, which is equal to 1 half. 1 third plus 1 fourth is greater than 1 half. 1 fifth plus 1 sixth plus 1 seventh plus 1 eighth is greater than 1 half, and so on. Therefore, we can continue this grouping indefinitely, and this infinite sum S would have to be greater than 1 plus the remaining infinite series, which is the summation from n equal 1 to infinity of 1 half, which we know diverges. So 1 plus a diverging series would also be diverging, and since the harmonic series is greater than this diverging series, the harmonic series diverges. So for example, summation of n equals 1 to infinity of 3 over n. So we can actually factor out the 3 and write this as 3 times the summation from n equals 1 to infinity So if we were to expand this, we'd have 3 times the harmonic series, which is 1 plus 1 half plus 1 third and so on, which we know diverges, and therefore 3 times the diverging series would also diverge. So we can say, since the harmonic series diverges, 3 times the harmonic series, which is equal to our series, also diverges. Example number 2. The summation of n equals 1 to infinity of negative 2 over n. Notice, each term in this series is going to be negative. But again, we can factor out negative 2 and write this as negative 2 times the summation of n equals 1 to infinity of 1 divided by n. So we have negative 2 times the harmonic series, which is 1 plus 1 half plus 1 third on. But notice how this series would approach negative infinity, not positive infinity, like the basic harmonic series. But either way, since we now know that the harmonic series diverges, negative 2 times our harmonic series, which is equal to our series, also diverges.